Okay, so our last part of plate tectonics is seismology, the study of earthquakes. And we'll start here with a couple little not videos, some pictures of the Northridge quake in Southern California. Occurred in 1994, had a magnitude of 6.7, shook for 15 seconds, killed over 50 people, over 9,000 injured, and $44 billion in damage. All right, some vocab terms. We've got what's called the focus or the hypocenter. It's the depth down inside the earth where the earthquake occurred. Okay, we got some shallow quakes and moderate quakes and some very deep quakes. We don't find any earthquakes deeper than 700 kilometers because it gets too hot and the rock becomes too soft. There's no friction, so there's no grinding of the rock, so there's no buildup of energy and no release. That isn't really that big a deal. The important one is this one, epicenter. Okay? This is what we're going to have to figure out. We're going to have to be able to figure out where the epicenter is on the surface of the earth. All right? All right, so start out with what kind of waves are we going to be working with? Earthquakes put out two main types of earthquake waves, P waves, compression waves. If you look here, what happens is as the wave moves through the rock, it compresses it and it stretches it out. It compresses it and it stretches it out. So we've got a longitudinal motion of the rock this way. All right? S waves, as the wave moves through longitudinally this way, the rock moves up and down or left to right sideways. All right? See if we can show this, if this will work. Okay? Yes. So you see how this is the P wave, how the wave moves through, the rock it's like a slinky. It stretches and compresses, stretches and compresses. All right? All right, the S wave is different. As the wave moves through, the rock moves up and down or side to side. All right? So it's like snapping a rope. All right? It's perpendicular to the motion of the wave. All right? All right, so P waves, this is important. P waves can travel through both solids and magma, okay? Solids and liquid rock. S waves can only travel through solids. All right, this is important because we need both P waves and S waves in order to figure out where an earthquake occurs. So if you lived on the opposite side of the earth from an earthquake, you wouldn't be able to figure out where it occurred because you wouldn't get any S waves because of the outer core being magma. The S waves get absorbed. They don't travel through it, right? And we need to know both what is the P wave and what is the S wave. We need to have both of those waves in order to pinpoint a location. And we're going to do that here eventually, okay? All right, so generally speaking, how do we find a location on Earth? So, for example, let's say, how do they find your cell phone? How do they pinpoint your cell phone? GPS, how does that work? All right, it's called triangulation. All right, so what happens is you have to have three different points of reference. If you have just one point of reference, you know how far away that you are from that one point, you get a circle with a radius of that distance around it. If you have 2 points, you end up with 2 circles that overlap. And if it has to be on both circles, it can only be where the 2 circles overlap. But it still only gives you 2 possible points. So now with the third circle, you can pinpoint an exact location. That's how GPS works. It figures out how far away you are from 3 different cell towers, and then it can pinpoint your location. Well, we're going to do the same thing with earthquakes. We're going to end up doing this, all right? So if you look at station A, if we know how far away station A is from the earthquake, we can map out that distance, and then that tells us that the earthquake is somewhere on this circle. Well, we add a second station in for that earthquake, and we know it's this far away, so that means it has to be on this circle. Once we have 2 circles, then it's either here or it's here. And then we add the third station, and so it allows us to pinpoint. That's called triangulation. We know how far away the earthquake is from 3 different cities. And if we know how far away it is from 3 different cities, we can find the location of that earthquake. All right, so here's how we're going to do it. We've got our 3 cities, Houston, Chicago, and Seattle. We have what's called a seismogram, all right? Over here at the beginning, you've got, this thing there's some background motion in the earth. It kind of picks up very small light motion in the earth. But as soon as it changes, That's the arrival of the P wave. The P wave is twice as fast as the S wave, so it's going to get to you first. So now we have the P wave that just went through. When it changes again, that gives us the S wave. All right? So we record what time the P wave gets there and what time the S wave gets there for each of 3 different cities. So if we look at this time scale, that P wave is going to arrive at 12:13 and 0 seconds. Okay, each of those bigger lines is a minute, 12:13 and 0 seconds. The S wave, 12:16 and 0 seconds. So we have the arrival time of Houston. Then we're going to get the arrival time for the P wave and the arrival time for the S wave for Chicago. Chicago's P arrival time is 12:15 and 0 seconds. Chicago's S wave arrival time is 12:19 and 0 seconds. And then we're going to get our third city. Here's our P arrival. Here's our S arrival. So the P arrival is easy. It falls right on 12:12 and 0 seconds. But look at the S. It doesn't fall right on the whole minute. It's not right on the 12:14, which is way down here, and it's not on the 12:15 either. It falls between them. And if you look, there are 3 blocks, 2 tick marks. Each of those tick marks is 20 seconds. So that would be 12, 14, and 40 seconds, separating those two. Once we have the arrival times for the P and S waves for 3 different cities, we can now use our reference tables to figure it out, right? To figure out the distance of those 3 cities to the epicenters. Here's how we're going to do it. I'm going to show you on this, and then I'll kind of show you on your actual reference table. All right, so here's page 11. Down at the bottom, we have a distance scale in 1,000 kilometers. So this is 1,000, this is 2,000, 3,000, 4,000. If that's the case, then each of these little lines must be 200. So that's 1,200, 1,400, 1,600, 1,800. There's 2,000, 2,200, 24, 26, 28, 3,000, 3,200, 3,400, 36, 38. You get the idea? All right, so each of those is 200. Now if we go up the side, this is our travel time in minutes. 1 minute, 2 minutes, 3 minutes, 4 minutes. So this would be 1 minute, 20 seconds, 1 minute, 40 seconds, 220, 240, 320, 340, and et cetera, et cetera. All right? So here's what we do with that information we have. I'm going to go with Houston because that's our first station. So we grab Houston. Now, first thing we do is we find the time difference between the arrivals. Now, since the S wave is later, we put that on top. It's a bigger number. Okay, we line up the S on top and the P arrival time on the bottom. We subtract them and we get 3 minutes. The S wave arrived 3 minutes after the P wave. That's called the lag time. Now we take a piece of scrap paper and we go down to our minute scale and we mark off 3 minutes of time. Now, keeping that piece of paper perfectly vertical with that grid, we're going to move it up the scale until the marks touch both lines. And then we're going to collect 2 pieces of data at this point. We're going to read down the scale vertically. And if we see where that arrow points, that's the tick mark right before 2,000, so that's 1,800. Then we're going to take the bottom tick mark where it touches the P line. See, here's our P wave line right there. And we're going to read across horizontally to get what's called the P travel time. And that is falling at 3 minutes and 40 seconds. So again, we take our 3 minute difference, we mark it using this scale, so we have 2 tick marks that are 3 minutes apart. We slide it up the scale until it touches both lines, read down to the bottom to get the distance to the epicenter, and then use the bottom tick mark and read to the left to get the P travel time. Those are the 2 pieces of information you need. All right? Now, we go to our table. We have to have a table to hold all this information in. All right, so we have our 3 cities. First thing we do is we punch in our P arrival times. We call that the clock time because that's what time the wave got to that city. All right, so P wave arrival, S wave arrival for all 3 cities, plug them in. All right, we said we took our difference. That's called our lag time. That's 3 minutes. Distance to the epicenter, we said was 1,800. P-wave travel time, 3 minutes and 40 seconds. So now we're going to do the same thing with Chicago. All right, I'm going to show you how to do Chicago real quick. 12:15 to 12:19 gives us 4 minutes. So we're going to put a piece of paper on here, mark 0, mark 4 minutes, and then slide it up until it touches both lines. See that? We read down, and it gives me 2,600 kilometers, and then we read across, and we get a 5-minute travel time. That's how you do that. All right? So, 4-minute difference, 2,600 kilometers, 5-minute travel time. And now Seattle's done the same way. The time difference is 2 minutes and 40 seconds. We mark 240 on our piece of paper. We slide it up the scale until it touches both lines. Read down to the bottom. We get 1,600 kilometers. Read across from the bottom tick mark, and we get 3 minutes and 20 seconds. All right. The origin time is what time did the earthquake actually occur. These are the times that the earthquake got to these cities. What time did the earthquake occur? And what we need is we need the P arrival time from one city, and we need the P travel time. If we know what time it got to Houston, and we know how long it took to get there, we can backtrack and figure out what time the earthquake actually occurred. All right? So we take the P arrival time, and we subtract off the P travel time. 12:13 and 0 seconds minus 3 minutes and 40 seconds gives us 12:09:20. All right? Now I'm going to show you that math. 12:13 and 3:40. Okay? 12:13. Oops, what did he say? 12:13 0. Yes, 12:13 0. Okay? Minus 3 minutes and 40 seconds. This is called time math. It's a little different from regular math. You have to think back to elementary when you learned how to borrow. All right? I can't take 40 seconds away from 0. I got to do all the seconds together, all the minutes together. I can't take 40 seconds away from 0, so I have to borrow 1 whole minute. Now that minute is equal to 60 seconds, so I take that 60 and add it to the 0 I already have, and oops, and now I have 60. Okay? 60 minus 40 is 20. 12 minus 3 is 9. Bring down the rest, and there's where I get my 12:09:20 for my arrival time, or excuse me, my origin time of that earthquake. All right? If we were together, I would be able to do a lot more practice with you right now, but this is just to kind of introduce you to it, and we'll kind of work on it as we go along. All right? All right, so now all we do is we take those distances, right? 1,800 from Houston, 2,600 from Chicago, 1,600 from Seattle. We draw circles around those cities at those distances. And then wherever they cross, in this case, they didn't cross in exactly one point. There's a little triangle right here, but we just picked a point in the middle of it, as close to where we can, where all three of them are meeting, and that's the epicenter of our earthquake.